So it's important now to discuss why delay in wires has become more important as transistors shrunk down. So when we talked about scaling MOSFET transistors, we found that as the dimensions of transistors decreased, their speed increased. Specifically, if the dimensions of a transistor, which includes L, W, and T oxide, shrink by a factor of K, and if all voltages, including threshold voltage, shrink by a factor of U, we found that the gate capacitance of transistors shrunk by a factor of K, while resistance remained pretty much the same. And this is true specifically for transistors where we suffer from velocity saturation or velocity overshoot, which leads to a behavior for the time constant where the time constant decreases by a factor of K. So as transistor dimensions shrunk, the speed of transistors increased by the same ratio that dimensions shrunk. So moving from 90 nanometers to 45 nanometers would lead not only to a decrease in the area of the circuit by a factor of 4, but also to an increase in speed by a factor of 2. Now, if we repeat this same analysis for wires, we will find that their behavior when dimensions and voltages scale is very different. For wires, we don't really need to care so much about voltage and how it scales, because resistance for wires is not a function of supply voltage. Resistance in MOSFET channels was a strong function of supply voltage. But again, if we have a wire which has a width of W, a thickness of TW, and a length of L, and if this is at a height of T above the substrate, then the capacitance is epsilon multiplied by W by L over T. Now, if we assume that every single dimension scales down by a factor of K, then C would scale down by a factor of the height above the substrate scales down by a factor of K, W by a factor of K, and L by a factor of K. Now this leads to a scaling down by a factor of K. Now resistance is L over sigma multiplied by the cross-sectional area, which is W times TW. Again, we are assuming that physical parameters like conductivity doesn't change, which is a correct assumption, and we are assuming that all dimensions are scaling down by the same ratio. So this leads to a scaling down of 1 over K in the numerator and 1 over K squared in the denominator, which leads to an increase by a factor of K. And so resistance increases by a factor of K. Now that means that the time constant for this wire is pretty much going to stay the same, and it's going to be RC, because capacitance decreases by the same ratio that resistance increases by. And so the time constant remains the same. Now, this doesn't mean that delay doesn't worsen for wires. It worsens in relative terms. It remains the same in absolute terms, but it is worse in relative terms because delay for gates has decreased by a factor of K. And that means that while gates keep improving, wires keep at the same level. And recall that moving from technology node to technology node, we are changing by orders of magnitude in terms of dimensions. And so this means that wires have kept pretty much at the same level of delay, while gates have lost orders of magnitude in delay, which we can imagine is obviously making wires more and more important. Now, there's another layer of complication here having to do particularly with the dimension of length. It is reasonable to assume that width will decrease as technology improves because design rules also decrease. It is also reasonable to assume that both T and TW are going to decrease as technology improves. But length is a different issue. As technology improves, the area of a chip generally increases, rather than decreases. And this is one of the reasons why we can pack more functionality into a chip from one technology node to another. It's not just because transistors are smaller, meaning we can pack more transistors in the same area. It's because area becomes cheaper in absolute terms, which means we can make bigger and bigger chips. But even if chips remain about the same area, this means that length does not scale down, because some wires used for routing are going to route between very long distances in different locations on the chip. These wires can be called global wires. And this is different from wires that are used to connect transistors within the same gate, or even, gates within the same module, for example, like this wire that's going to connect two gates. These global wires are used in placement and routing to connect cells that are really spaced far apart. And so for these wires in specific, we cannot assume that L scales down by a value of K. In fact, we'll assume that L scales up by a factor of KW. And this factor could be greater than 1. In a lot of cases, actually, it is. So if we look at what happens to capacitance in this case, so epsilon WL over T, this is gonna, epsilon is not gonna scale down, right? So epsilon is not gonna scale down. W is gonna scale down by a factor of K. T is gonna scale down by a factor of K. But L is gonna scale up by a factor of KW, which means that C for the wire scales up by a factor of KW. And if we look at R resistance, it's L over sigma WTW. So L is going to scale up by a factor of KW, and each of these guys are going to scale down by a factor of K, leading to a total scaling down in the denominator of 1 over K squared. So in the numerator, this is going to be K squared. Now, if we look at the time constant for these long wires, we find that when we scale down, the time constant is not going to improve or even stay the same. In fact, the time constant is going to be KW squared multiplied by K squared multiplied by the time constant. So, of course, if KW is equal to 1 over K, that leads to a scaling of 1, meaning that the time constant is back again to not scaling at all. But if KW is greater than 1, then we see that the time constant starts to worsen, and significantly so. And recall that K itself is a number greater than 1, which is why we will suffer a lot if KW is anything close to even 1. This would lead to a quadratic increase in delay. And if we look at how capacitance behaves and how resistance behaves, we find that the main culprit in this bad behavior is actually resistance rather than capacitance. Resistance worsens substantially relative to capacitance. It worsens cubically, whereas capacitance worsens linearly in this case. And the reason for this is basically because resistance is a function of the cross-sectional area, which decreases, and it decreases through both of its dimensions, Tw and W. And because L is also increasing, or at least not improving, so every single aspect of resistance is leading to a worsening value, an increased value. So our main problem here is with wire resistance rather than wire capacitance. So we have to make some changes to the way we scale wires, otherwise they would dominate delay very fast. And if we look at W, we find that we have to scale down W by a factor of K. We have to scale it down as fast as technology scales down. And the reason for that is that if we don't scale W down as fast as technology, we increase capacitance. So that's a problem. And also because if we don't decrease W, we will not be able to pack wires close together, and therefore we will not be able to do routing properly. And gates will be much smaller than wires, and we will be wire limited rather than gate limited. We cannot also scale down L because L, again, is determined by placement and routing and determined by the size of the chip. We can, however, not scale down TW as fast as everybody else. Because if we keep TW relatively high, if we keep the wire relatively thick, then we can control the way that resistance for the wire decreases and perhaps improve how resistance and capacitance and time constant in general behave. So the whole idea here is that we are assuming that when we scale down, we're going to scale down everything, including TW. But what if we scale down everything except TW? Perhaps keep TW at the same level or scale it down slower, or maybe even theoretically make it thicker. So in that case, how would the behavior of the time constant improve as we scale down? So here we're going to assume that L is going to scale at a factor of kW for long range wires and a factor of 1 for short range wires. We're going to assume that T and W are scaling down with the technology parameter 1 over K, but the TW, the thickness of the wire, is actually scaling down at a slower rate than other dimensions, and we're going to assume that it is scaling down at a ratio of 1 over KT. If KT is equal to 1, then we are not scaling down wire thickness at all. If KT is less than 1, then we are actually making it thicker. But it doesn't have to be either 1 or less than 1. It could be greater than 1, but still smaller than K, meaning that we are scaling down the thickness, but not as fast as everybody else. So let's trace that again. For short range wires, C is epsilon WL over T. Now, we are going to assume everything scales down to the factor of K because we are a short range wire, so that's 1 over K. R is L over sigma WT W, and so L is scaling down to the factor of K. W is scaling down at a factor of K again, and TW at a factor of KT. So then that leads to a scaling up at a factor of KT. So resistance scales up at a factor of KT, which leads to a time constant scaling at a factor of KT over K. So we are scaling the time constant at a factor of KT over K, which means that the time constant is when KT is equal to K, the time constant doesn't change at all, which is the original case where we were scaling down the thickness of the wire as fast as we are scaling down everything else. If KT is smaller than K, then the time constant is actually improving because KT over K is a ratio smaller than 1. And that would be a case where we actually see wire delay improving. But again, it will not improve as fast as gate delays. The only case where it would improve as fast as gate delays is if KT is equal to 1, which means that we are not actually making the wires any thinner. We are reducing all other dimensions, but not wire thickness. Now, this is true for short-range wires, where L changes to the factor of K. This is 1 over K, of course, not 1. But for long-range wires, where L is actually scaling up, probably at a factor of KW, we have to repeat this again. And so C would be proportional to 1 over K for W, KW for L, and 1 over K for 1 over KT, actually, 1 over K, no, 1 over K for T. So this would be KW. So C is proportional to KW. This actually shows that capacitance is not affected at all by the decision to change how wire thickness scales. And we have to discuss this because there's an assumption here. Resistance is L over sigma multiplied by WTW. Now L is scaling up at a factor of KW, W is scaling down at a factor of K, and TW is scaling down at a factor of KT. Now that means that we are scaling at a factor of KW, K, KT. And the time constant is scaling at a factor of KW square, K, KT. Now, if KT is equal to K, we go back to the situation where we are scaling up with a factor of KW square, K square. But if KT is equal to 1, which is the best we can do under reasonable assumptions, then time constant is increasing at a factor of K times KW square. So in all cases, the time constant is going to increase, but we at least are keeping it from increasing at a power of 4. Rather than that, we are making it increase a little bit slower. Now, there's a price to pay for this, because if you are bringing wires together when you scale technology, but keeping their height, their thickness relatively thick, then first of all, you increase interwire capacitance, and you also increase fringing capacitance to substrate. So these are real issues, like these are severe issues. Fringe capacitance substrate increases capacitance, total capacitance seen by the wire, and worsens the time constant. The interwire capacitance is even more dangerous because it leads to signal integrity issues through crosstalk. So what practically happens is that the way thickness for wires is scaled differs based on the layer of metal wire we are using. So that upper metal layers are usually thicker and lower metal layers are usually thinner. On the other hand, lower metal layers are usually packed closer together and upper metal layers are kept farther apart through design rules. This guarantees that we have wires with reasonable resistance in the upper layers and that we have wires with reasonable density in the lower layers, and that crosstalk is reduced for these higher layer wires by keeping them apart, and fringing capacitance is also reduced by the fact that these wires are much higher above the substrate. Now, the placement and routing tool has to be intelligent and has to use lower level metal layers to do local routing or short range wire routing, while using upper metal layers to do long range wire routing.